Alright guys, I want to work through
But their live is right next to them. But Ayersville and Napoleon have their own team.
Alright, so I want to prove that oh, you guys can't see it. I want to prove that. You guys proved, or we proved, the cosine formula yesterday, right? Okay. So that wasn't too bad, but it involved a lot of geometry, right? This one doesn't involve much geometry, but it does involve us knowing some identities. Okay. The number one identity that this involves is the fact that the sine of theta is equal to the cosine of pi over 2 minus theta, right? And it's also eventually going to incorporate the fact that cosine of, let's say, we still say theta, is equal to the sine of pi over 2 minus theta. Okay? Remember, graphically, this will load. Come on. There we go. Remember, we've got the sine of x and graph the cosine of pi over 2 minus x. It's nothing different, right? Okay. If we have the cosine of x and graph the sine of pi over 2 minus x, we should get something to land on the blue here, and we do. Okay. So these two are the same. These two are the same, right? That's exactly what we're saying right here. Okay, so we're going to need those 2 points here in a moment to prove this. If I want to start with the sine of alpha, or A, I guess, plus B, and I'm going to rewrite that. I'm going to say that is equal to the cosine of pi over 2 minus A plus B. That is this first line here. Okay, it's that first blue statement, because A plus B is just the alpha, A plus B is just the theta. Does that make sense? A plus B is just the theta, so I just replace theta with A plus B. Okay? Now, there's some algebra there that we should probably take care of. Is this the same thing as cosine pi over 2 minus A minus B? Is that right? Now, if I was running through that, order of operations would tell me to do what subtraction first? It would tell me to do that first, right? So let's group it that way. And now, does that present the sine of A plus B in terms of cosine? Yeah. And now and it's a sum or difference of cosine, right? And we proved that formula yesterday. We know that formula exists. So let's go ahead and run that formula, or this through that formula. Cosine, remember it goes cosine of the first angle, cosine of the second angle, right? And then it's the same sine, let me rephrase that. It's cosine, so it's a different sign of that, so it's going to be plus. And then it's the sine of the first angle, sine of the second angle? Well, the first angle is pi over 2 minus A. And then the second angle is B, right? Okay with everybody? Okay. So now, let's kind of work our way backwards a little bit. Cosine of pi over 2 minus A is right there, right? So I can rewrite that as sine of A. Cosine of B plus, okay, sine of pi over 2 minus A. Sine of pi over 2 minus theta is the same thing as cosine theta, right? So this is cosine A. And this is sine B. And you see then that sine A plus B goes to sine A cosine B or plus cosine A sine B. So you go sine, cosine, sine, cosine, sine. And that's what we said, that's what we defined it as a couple days ago, right? Okay, so that's, there's multiple substitutions there of the same thing though, right? Okay, we need that one identity, sine theta equals cosine pi over 2 minus theta, and cosine theta equals sine pi over 2 minus theta. But once we have those cofunction identities, which we know are true because we've seen it with the right triangles, we've seen it with graphing them at the beginning there, their transformations of one another, so they are true. We can use those then to create this new formula for sine of A plus B. Okay, is that doable? All right, so now let's work through and figure out what then is the tangent of A plus B. And this, guys, is the reason I keep telling you not to memorize things. Because I always get confused with, I know it goes tangent A, tangent B up top, but I can't remember if it's a plus or minus. And then it goes 1, and then it goes tangent A, tangent B on the bottom, but I can't remember if it's a minus or a plus on the bottom. Okay? But if I know that tangent of A plus B is simply sine over cosine. Sine of A plus B sine of A plus B over cosine of A plus B. And I know a lot of you already, you're sharing with me that you're knowing these. You've memorized these, which is great. You know the sine of A plus B is sine A cosine B plus cosine A sine B. All over then, cosine A plus B is cosine A cosine B minus sine A sine B. So now I know that with the tangent rule, the numerator is actually stuck together with a plus sign. The denominator is the one with the minus sign when it's tangent of A plus B. Now, if it's the tangent sum and difference formula, it would be convenient if tangent showed up on the right-hand side, right? Okay. So what we can do is start thinking about, adjusting this and going through and trying to decide which of those four objects could I divide by so that tangent shows up conveniently in several spots. And it turns out that after a little bit of trial and error of what to divide by, you would find out if I divide everything by that right there, cosine A, cosine B, divide that by cosine A, cosine B, and we can do this. Think about why we can do this. If I multiply this bottom by 1 over cosine A, cosine B, and I multiply the top by 1 over cosine A, cosine B, that is effectively dividing. So if I took this, just look at the red stuff, if I took this blue thing here and distribute it through the red stuff, is it going to give me what I have written here in red and blue? Okay, so I'm distributing this to the numerator, distributing the same thing to the denominator. What have I effectively multiplied by here? What's 1 over cosine A times cosine B divided by 1 over cosine A, cosine B? It's just 1, right? So we've essentially multiplied by 1, so we're allowed to do that, okay? So I just want to make sure that we understand that I'm not breaking any algebra rules when we just start dividing by anything we want to, because we're dividing everything by the same thing in this expression. So it's just multiplying by 1. Well, that would be different if it was, working in an equation or something like that, right? Okay, so we're just adjusting this expression. Okay, so let's kind of work through this and see what we get. What's sine A divided by cosine A? If I look at those two right there, what's that going to give me? Tangent A. Okay. What's cosine B divided by cosine B? 1. So we have tangent A times 1, right? Just tangent A. What's cosine A divided by cosine A right here? 1. And what's sine B divided by cosine B? Tangent B. Okay. Just a side note, hopefully it makes sense to you that if I had sine A over cosine B, is that going to divide to anything? The arguments are different, right? That would be a problem. So that's not going to go tangent of anything. So that's kind of why we divided by cosine A, cosine B, because everything lines up real nice here. If I take cosine A divided by cosine A, gives me 1, right? Cosine B divided by cosine B gives me another 1. So it turns into a 1. 1 times 1. Sine A divided by cosine A is tangent A. And sine B divided by cosine B, tangent B. And now we have found that tangent of A plus B is equal to tangent A plus tangent B over 1 minus tangent A, tangent B. Okay? Now, if I wanted to find tangent of A minus B, we could either substitute sine of A minus B over cosine of A minus B and go through the whole process again, or I could rewrite tangent of A plus B as tangent of A plus the opposite of B, and then wherever it gives me tangent of opposite B, I essentially go through and I negate that because tangent of the opposite B is the same thing as the negative tangent B, because they're even odd identities. And what that's going to do, if I go tangent of A minus B, that's going to turn into tangent A minus tangent B on top, divided by now 1 plus tangent A, tangent B. Okay? Ultimately, the way if I'm going to try to develop a way of memorizing these somewhat, okay, again, and that's something to think about. If we're doing it, sometimes, obviously, I say, learn the relationship, right? But as we do enough, you're going to memorize it for the short term, right? Okay, but eventually that short term will wear off. But the hope is that you still have in the background somewhere that relationship that when you do need to develop this again, you can. So, and that, obviously, I think I'm a little bit different because I teach this every year, right? I've been doing it for 12 years. If you would have asked me, 3 weeks ago, Mr. Fay, tangent A minus B, give it to me right now. I'm not going to be able to give it to you right now, okay? I'm going to have to go through the proof real quick, right? Okay? But I'm going to know that proof. That's the thing that I'm trying to get you guys to realize. Because I know the relationships, okay? And that's, I think, what is very, very, very important. When we're trying to maybe learn these or remember these on the short term, obviously whatever that sign is right there, it's the same up top, and it's opposite on the bottom. Okay? Some textbooks, I hate this because people they don't pay a whole lot of attention to the order of the plus or minuses. If I write the plus or minus this way, when I write this as tangent of A tangent of B on top. Notice that these signs are the same, right? So then up top, it's got to be plus or minus, just like I wrote it here. But when I go on the bottom, it's got to be that sign and that sign are opposites, right? So these kind of have to be opposites. So on the bottom, it's going to be a minus on top and a positive on the bottom. And then tangent A, tangent B. And all too often, people will read this, if it's all written at once, they will read that, that, and that all as the same symbol, where it's not, right? Does that make sense? Okay. I prefer to teach it and learn it as two separate ones, and you learn the plus and minuses the correct way, and you don't make that mistake of just making the assumption that those are all the same symbol. There's a very easy error to make. So what's nice about that, guys, is if they ask me, what is the tangent of 105, you can now rewrite that as tangent of 60 plus 45, right? Okay. And the quick then way of doing this, so it's going to be this rule here. We got tangent of 60 plus then the tangent of 45 all over 1 minus tangent 60 tangent 45. And now what's nice about this, what's the tangent of 60? Anybody know that? And, okay, so you go sine over cosine. So the sine of 60 is what? Radical 3 over 2, right? Okay. The cosine of 60 is 1/2. If I divide those, I get radical 3, right? Okay. So this turns into radical 3. The way I remember it is that 30 is radical 3 over 3, right? So 30 has that 3 in it, so the answer, the evaluation has that extra 3 in it, radical 3 over 3. 60 doesn't have that, so 60 is just the radical 3. Okay? It's a weird way I think of remembering it, but it works for me. So 60 is radical 3. What's tangent of 45? Yeah. So I got radical 3 plus 1 over now 1 minus radical 3. Okay? That would be the exact value of tangent of 105. If you type that in your calculator, okay, tangent of 105, make sure we're in degrees here, gives me that number there, okay, and what I say, 1 plus square root of 3 over, oops, was it square root of 3 minus 1? No, 1 minus that, right? So we do see that those two things are the same. Okay. Now, you might be a person who says, I'm not going to use that formula at all. Because if they ask me tangent of 60 plus 45, can I rewrite that as sine of 60 plus 45 over cosine of 60 plus 45? And then rewrite my sine of 60 plus 45 rule, rewrite my cosine of 60 plus 45 rule, get a numerator, get a denominator, divide them out, you get the same thing. Okay? So it's up to you. I'll leave it, one way or the other does not matter. Okay? So that's the derivation of those two formulas. Let's do some practice. I think, did you see some of these in your homework? Like that one there? I think that's the hardest problem. You haven't seen, there's not one of those in your homework yet? Okay. You will eventually. I think that's the hardest problem we've seen so far, maybe in the entire year. Okay? This is going to hopefully, I got them in kind of a backwards order, but hopefully this gets us to understanding question 7, or example 7 a little bit better. Okay? When I look at this, okay, I'm going to draw a picture. You don't necessarily need the picture, because my hope is that when I ask you what the cosine inverse of radical 2 over 2 is, essentially you remember that radical 2 over 2 is a ratio, right? The ratio of adjacent divided by hypotenuse in this case. And I hope that you know that when I say cosine inverse of radical 2 over 2, that's going to spit back an angle, right? What angle is going to spit back? 45, okay? So So I hope we know that. But if I drew a picture, what this is providing, remember that's a ratio. So it's giving me the adjacent side to be radical 2, this side to be 2. That's the hypotenuse, right? If I go through the Pythagorean theorem with that information, it's going to give me that to be radical 2. And now I hope you see that that's a radical 2, or an n radical 2, an n, and an n. Does that make sense? So that has to be a 45-degree angle. So my hopes are that you see that those ratios, the cosine inverse ratio here is going to produce some angle. So in this case, it produces 45 degrees. Okay? So that thing right there goes at 45 degrees. Now, especially because we just did it, tangent inverse of radical 3, what angle is that going to give me? Should give me 60, right? But if I didn't know that, looking at my picture, tangent is opposite over adjacent, right? Radical 3, there's 1. Pythagorean theorem would say that would be 2, right? Is that not the template for a 30, 60, 90? And across from the radical 3 side is always 60 degrees, right? So tangent inverse is 60 degrees. My hopes in understanding this question, and in the example 7 that we're going to do in a moment, is that when they give me cosine inverse of something, whether it be numerical like it is here or variable like it is in question 7, they are providing me that picture. They're providing me an angle. Does that make sense? Okay. So now if we got sine of 45 plus 60, we're going to rewrite that as sine 45 cosine 60 plus cosine 45 sine 60. That's the sum rule for sine, right? What's the sine of 45? Radical 2 over 2. Cosine 60? 1/2. Cosine 45? Radical 2 over 2. Sine 60? Good. So now this is going to evaluate to radical 2 over 4, radical 6 over 4. So I'm going to write the final answer that way. Okay? Which, if you remember back to probably Friday, maybe, we did that one. I asked you what the sine of 105 was, right? And we broke it up to 45 plus 60, and we came up with that number right there, which is great. Okay? Let's check this. I want to check this because of how we're going to check question 7. But you should always be able to go back and figure out, okay, if I just found square root of 2 plus square root of 6 divided by 4 as that number right there, doesn't that mean that the sine of the cosine inverse of square root of 2 over 2 plus the tangent inverse of the square root of 3 should be the same number? All right, so this is what we started with. It's actually 0.9659. This is what we evaluate to be the same thing, right? Okay. Questions on that? Does that kind of make sense? Okay. Now, let's make it more abstract. Let's take now, I think the next question actually flip-flops the sine and cosine. Okay, so now the outside function is cosine, this inside function is sine inverse. So they're not exactly the same question, but it's the same concept. Okay, but now look at that. That example at the top, the argument for sine inverse is unknown, right? The argument for a tangent is an unknown, right? Okay, so this is going to work. This is going to basically do for us what number 8 was doing, but it's doing it for all values instead of just specific values like radical 2 or 2 and radical 3. Okay? So, can I start this off the same way we started the last one? The sine inverse, this thing right here, is going to provide an angle. That is the ratio of the opposite side divided by the hypotenuse, right? Okay. Now it's a little abstract, I think, here, because it's x over 1. Okay. So if I draw a picture, okay, the sine inverse is going to give us back something in the first or fourth quadrant, right? Okay. I'm going to, just to make things easier, make the assumption that it comes back from the first quadrant. If the ratio of the opposite side divided by hypotenuse is x over 1, I get that, right? Okay. And that obviously also, I think, maybe tells us that we should be in the first quadrant, because if it was negative x, it would be down here, right? Okay. So does that then allow me to come up with what this side here is? Isn't that side, using the Pythagorean theorem, going to be the square root of 1 minus x squared? That make sense, everybody? Okay. That's just saying, you know, if that's, let's just call that a, I'd say a squared plus x squared is equal to 1 squared, and then just solve for a. So it'd be a squared is equal to 1 minus x squared, and then square root both sides, and it gives me exactly that, right? Okay. Well, remember in the last question, that radical 2 over 2 gave me that to be 45. I still don't know what that is, because I don't know what these letters are. I don't know what x represents, right? Let's just call that theta. It's giving me that angle theta. Okay. So this thing here provides me theta. So I'm going to rewrite this as cosine. Instead of sine inverse of x, it's theta. Okay. Now, encapsulated inside that theta is that picture too. Does that make sense? So we're going to come back to that picture here in a moment. You need that. You can't just say, oh, well, every time this happens, it just changes sine inverse of x to some Greek letter. I'm going to choose what Greek letter I want and be done. You can't, because you need that picture for the next step. Okay? I now need to do the exact same thing with this. Okay? So we're going to draw that picture. And the tangent inverse gives back the same values that the sine inverse does, the first and fourth quadrant. And it's a positive y, so I'm just going to make the argument that this is y, and that's 1, right? Opposite over adjacent. Okay? Making then this Pythagorean theorem would be 1 plus y squared underneath the square root, right? A squared plus b squared equals c squared, so square root everything is this. That picture produces that angle. Let's call that angle phi. So we get something like that. Now, that looks like a formula that we've been dealing with, right? Let's replace that. Let's expand that into cosine of theta, cosine of phi, plus sine of theta, sine of phi. And now here's the purpose of the pictures. In my picture, what is the cosine of theta? It'd be, all right, it's the radical 1 minus x squared over 1, right? What is the cosine of phi? All right. And now, if I go to sine of theta, that's nice. That's just x, right? X over 1. And the sine of phi, okay. Now that's ugly, but it can get a little bit better. Obviously, this is going to be root 1 minus x squared over root 1 plus y squared, right? You could put that in 1 square root, but I'm going to avoid doing that because of what happens over here. What do I recognize about those two denominators? They're the same, so it makes more sense, I think, to write this as xy plus root 1 minus x squared all over that root 1 plus y squared. Where if I would have put this underneath one root, I can't then combine those fractions, right? Ultimately, it shouldn't really, just the way it looks, I think that looks nicer at the end than anything. But what that does then for us, guys, is it gives us the x and y, so maybe x is radical 2 or 2, maybe y is radical 3. And it gives me the formula to evaluate that much quicker than trying to pick things off the unit circle. Does that make sense? So if I were like writing a computer program and I needed this thing to evaluate these types of things all the time over and over and over again, I wouldn't write that program to reference the unit circle over and over again. I would write that program with that formula at the bottom. And now it's just picking off x's and y's that maybe the user defines or something like that. Okay? And it would allow that thing to operate much quicker. So let's see if this actually makes sense. Let's go to Desmos, okay, and let's type in what we started with. So we started with the cosine of the sine inverse of x minus the tangent inverse of y, okay? Now when I type this in, it's looking for an equation here. If I click on this, it says try adding equal signs, turn this into an equation. I don't really want to do that, okay? But I want to evaluate this thing in x's and y's. But the way Desmos or GeoGebra is set up with x's and y's are for graphing, right? Okay? So we're going to, in a moment, come back and change those x's and y's to something different, okay? The other one we had was xy plus square root of 1 minus x squared over the square root of 1 plus y squared. Is that right? Okay. All right. So same thing. Ask me to graph that. If I put, let's just see what happens here. If I put y equals there, come up here, put y equals. Are those two graphs on the right-hand side the same? Colors are stupid. But you see that they are the same, right? So that might be proof to you that, yeah, we've got the right thing here. But let's, instead of graphing, because if I were to graph this, let's say you only had your TI 8384. Is that a nightmare to graph on TI 8384? Yes, okay, because it's an explicit equation, right? Or sorry, that's an implicit equation, and your TI 8384 set up to type in explicit. So that's an issue. So this is what we want to do. I'm going to take and rewrite x as A and y as B. Okay? So then x was A, y was B, x was A, y was B. Does that make sense, everybody? Okay, now, right now, if I start doing this, there are going to be places where this is undefined and we have issues, right? Okay? Think about what A and B are. Sine inverse of A, you're only allowed to put A values in that are between what two numbers? Negative 1 and 1. Okay? So A only oscillates between negative 1 and 1 because of the arc sine of x. If I were to graph that, what's going on? Arc sine of x is just that, right? I was in degrees. Arc sine of x is just that, between negative 1 and 1, right? Okay. Arc tangent of x can be anything, right? The domain is anything. So that, well, I don't care about B. B doesn't need to be adjusted. But now if I scroll through here, make that 1. Now if I scroll through here, well, that's stupid. I set the step wrong too, didn't I?
Yeah.
I think if I just delete the step, it'll be okay. There we go. I never get an undefined there, right? I never get an undefined there. So now I'm seeing that with an A value of 0.56 and a B value of negative 3.8, do these two things evaluate the same way? Yes. I can flip-flop them to whatever I want them to be. Do they still evaluate the same way? So is that a conclusion that we can argue that, yes, this is the correct evaluation or simplification of that original trigonometric function? And that's nice because now, guys, we have removed the trigonometric aspect of things, and now it's just a algebraic function, right? Okay? Which, calculus-wise, might be a nice thing for us to be able to do. Okay, so let's try something here. Let's do this. And this is going to kind of introduce us into what I want to start with tomorrow. If I go sine, you guys know what sine of alpha plus beta is. Let's go to this. Let's go sine of theta plus theta. And let's expand that. So sine of a sum goes sine, cosine, plus then cosine, sine, right? And then in those arguments go the two objects that were here in that order, correct? So it just goes theta, 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 right? Okay. So what's sine theta, cosine theta, and this thing here, what are they to one another? Well, the same thing. So how many of them do you have? You have two. 2 sine theta, cosine theta. How can I rewrite this thing? Sine of 2 theta. Sine of 2 theta is what we call a double angle, obviously because we're taking the angle and doubling it, right? So there is the double angle formula for the sine function, okay? Meaning that if I wanted to find the sine of 60 degrees, I can do that now by just knowing what the sine of 30 is. Okay, Sammy?
How is it not 2 cosine?
What do you mean 2? Because this is a product. So you don't want to go 2 sine theta, 2 cosine theta, right? It'd be like xy plus xy. That's going to be just 2 xy's, right? So here's kind of an example. If I said sine of 60, you guys already know sine of 60 is radical 302, right? Okay, so the reason I want to do this is because I already know the answer. So if I can reproduce radical 302 a different way, I know that this formula works. So can I take sine of 60 and rewrite that as sine of 2 times 30? Now, the reason I do that is because now my 30 is the theta that's in my formula, right? So now I go 2 sine of theta, which is 30, cosine theta, which is 30. Does that make sense to everybody? Okay. So I go 2, what's the sine of 30? 1/2. What's the cosine of 30? Right, 302. What's the 2 and 1/2 going to do? And you're left with just radical 302. And that's what I'm saying is sine of 60, right? We already knew that. Okay? So that is, and it's just one situation, it's one instance. But you could do it with sine of 120, make it 2 times 60. You could do it with the sine of 180, make it 90 times 2. You can do it with anything off the unit circle that you can double, and you'll find out that you get the same result back. Okay? Now, is that useful for a unit circle? Because when we did the sum and difference, you think about the sum and difference, didn't it give me now exact values for like 15 degrees? And it gave me exact values for 75 degrees. And then 105 and 165 and so forth, all the way around the unit circle. But it gave those new angle measurements on the unit circle. Is the double angle formula for sine ever going to give me something new? No, because if I start with 30, it's going to give me 60. I start with 60, it's going to be 120. Okay, I start with 90, it gives me 180. Start with 45, it gives me 90. Start with 15, it gives me 30. Start with 75, it gives me 150. And those are all the ones that's given me. Those are all ones we already knew, right? So it's not providing anything new, but what it does end up allowing for us is later on when we introduce equations, which we're getting really close to, you're going to see a lot of equations that have like sine of 2 theta in them and a cosine of just 1 theta. Well, when we have equations that have varying arguments of 2 theta or theta or 3 theta, we can't solve them until they're all the same argument. Does that make sense? So this allows us to kind of reduce an argument that is bigger than 1 down to arguments that is 1 theta, or that are 1 theta. So that's a nice thing there. We'll stop there, you guys. We're running out of time. So tomorrow, we'll start with this again, just to reiterate what that formula is, and then we'll say, okay, well, it's cosine theta plus cosine theta. Or it's cosine theta plus theta, okay? And work through that formula and see what the cosine double angle formula looks like, okay? And then obviously you can do the work with the tangent double angle as well. I had several people wanting the homework extended.